Prerequisites for network analysis or network theory. Network analysis or network theory. So in today's lecture, we will be discussing some basic concepts. Those are needed for the study of these two subjects. These two subjects are generally found in the second year engineering in the branches electronics and electrical engineering. So most of the students, those have the background of diploma, they already studied some basic concepts. Those are needed, or some requisites, those are needed for these two subjects. So in today's lecture, we just revise those requisites. So in today's lecture, we will be discussing what is EMF. Basically, the first part we will be discussing DC supply. Second, we will be discussing current, then resistance, then connection of resistance or combination of resistances or combination. That is basically series and parallel. So this will be the lecture flow. So first of all, we will discuss the process of conduction and what is conductor, what is insulator and all that. So all of us know very basic about the conductors. All of us know that conductors are having free electrons. These free electrons are randomly moving in all possible directions. So they are moving like this in all possible directions. But if we connect some supply, we connect a battery, DC supply for example, battery in this way. In that case, the electrons from minus of the battery will enter into the conductor, and these all electrons which are actually moving randomly will start moving in particular direction like this. And this will form current. So basically, current means flow, just like a flow of water. Here we say it's a flow of electrons. So electrons are moving in particular direction, forms a current. What was the reason of current? Yes, we should apply the supply. This type of supply, which is having polarity fixed, known as a DC supply. And this type of current, which is moving in one particular direction, is known as a DC current or direct current. Okay. In the future lectures, we will be discussing AC fundamentals as well. But in today's lecture, we will be just talking about the DC supplies. Anyway, so this is about the process of conduction. You can, if you want to go in details of this, you can see another video where I will explain the process of conduction in very much depth. So in today's lecture, this is not our major role or major topic of discussion. First of all, what is EMF? This EMF, you can say the long form is electromotive force. So, if you consider a battery, a DC supply, almost of students have seen the batteries in mobile phones, inverters, and in so many day-to-day instruments. You see this battery. So it is a DC supply. It has got polarities plus and minus. In simple, I can say minus means what? Something where we find excess electrons, and plus is something where we see deficiency. Now, what is the reason of this excess electrons and deficiency of electrons? You see, some chemical action is going on inside, and due to that, somewhere free electrons are produced and somewhere deficiency is there. Somewhere excess electrons, somewhere deficiency. If you connect these two terminals with the help of some conductive path, you will observe that electrons from minus, that is excess side, will just try to travel towards the deficiency side this way. Okay, so this will just complete the flow of current, or this is just what you can say, path is completed. So electrons from minus always try to travel towards the plus, but they need a path, some conductive path. So this may be some conductor here which allow electrons to flow. Now why this conductor allow electrons to flow? Because it itself is having free electrons. These free electrons will start traveling and new electrons from minus will take their places. In this way process of conduction is established. Now our discussion is what is the EMF. So you can say some kind of force is present here. That force is responsible for movement of electrons. You can just compare this with system like this. Suppose I have some pool of water here and I have some motor. I have some arrangement like this, a pipe here and like this here. Suppose if you start this motor, what will happen? This water will be lifted and so water will just come out in this way. And here I can have some bucket, that bucket will get filled with the water. This is just a flow of water, we can say. We can just assume this has a minus, this has a plus. So here from minus it's an excess of water. This is lifted and it is just thrown towards the plus. Who is responsible? This motor is responsible. Similarly, same role is done by the battery. What I can say, from minus, electrons are thrown towards plus, but it needs a proper path. Here, even air can be a path. Now, what are the obstacles? Obstacles like resistance offered by this pipe or resistance offered by the air. This may be the obstacle. What I can say, this is a source, this is a destination. So water travels from source to destination. So here electrons travels from source to destination. And the force here is what? Motor is giving the force. So here this battery is the force. Now what is force? Now you can say, I will just define the EMF. So EMF is basically energy supplied to circulate unit charge once round the circle. Let's just discuss this. See, energy. Will supply energy? Cell will supply energy. Now what is circulated? Charge is circulated. Now what is my unit charge? I can say unit charge means 1 coulomb charge. How do what is the 1 coulomb? See, from chemistry we have seen that electron is negatively charged particle. Each electron carries 1.6 into 10 raised to minus 19 coulomb charge. Now when I say 1 coulomb, actually how many electrons? That figure will be very large. It will be 1 upon 1.6 into 10 raised to minus 19. So it is 1 upon 1.6 into 10 raised to plus 19. So this figure will be somewhere 6.63 into 10 raised to 18 or something like that. Anyway, so we don't want an exact figure. So this is very large. So when I say these many electrons from minus travel from minus to plus, that is circulated round the circuit. Okay, I say unit charge is circulated round the circuit. Now who will circulate that unit charge? Battery will circulate that unit charge. So the energy is supplied by the battery. Now we are interested how much energy supplied for the circulation of unit charge. That is what the EMF of the cell. If suppose I say 1 volt is EMF of the cell, it is something 1 joule on 1 coulomb. Means when 1 coulomb charge is circulated, that is it is traveling from minus to plus, that is these many electrons travel from minus to plus. How much energy supplied? 1 joule energy is supplied by the cell. If suppose EMF of the cell is 2 volt, what I can say, it is something 2 joule on 1 coulomb. See here, same charge circulated, in same number of electrons circulated from minus to plus, but here it is 1 joule energy, here it is 2 joule energy. See, energy is more. Okay, you can say that electrons will travel with larger velocity. This is actually something a drift velocity. So electrons will travel with larger velocity. So more number of electrons will travel in the same time. Okay. Anyway, so if in that case what we say, force is more. Now just compare with this system. If force is more, what will happen? You can say the flow of water will increase, and this bucket will get filled, in a less duration of time. Okay, you just compare with the force here. If force increases, more amount of water is thrown in given time, so it will take less time for this bucket to get filled with water. Similarly here, if force increases, what will happen? More number of electrons will travel. Ultimately what I can say, more number of electrons means current will increase. So what I can say, if EMF is more, current will increase. Now where is EMF? Now see, actually we can increase the EMF of cell by cascading number of cells. Generally when I say 12 volt is the EMF of the cell, actually this 12 volt battery will be the combination of 1 volt cells connected in cascade. So there will be 12 cells inside that will form a 12 volt EMF battery. Okay, if I say 6 volt battery, there may be 6 standard 1 volt batteries cascaded inside. In this way, increasing EMF ultimately increases the current. Now what is current? We can say current is something amount of charge traveling through given cross section in unit time. Means what? Actually current increases means flow increases. You can observe more water is coming out in a given, you can say you can take a unit time. You can say 1 second. You will measure how much water is coming out of it, 1 second. If more water coming out of it, you will say current is increased. Similarly, in case of conductors, suppose I have this conductor here, and just consider a cross section, and I will measure how much charge is flowing. How much charge means actually how many electrons are flowing, because each electron carries this much charge. When I say charge is traveling, actually electrons are traveling. So I will just observe how much charge or how many electrons traveling through this cross section in 1 second. That will give us the charge traveling through given cross section in unit time. That is what the current is. So current is defined as Q upon T. Now how you calculate Q? Actually N into 1.6 into 10 raised to minus 19 upon T. What is N? Total number of electrons traveling in a given time. So in 1 second, then I say 1 ampere current is flowing. Actually I say 1 coulomb on 1 second. Means what? If suppose 1 coulomb charge is traveling in 1 second through given cross section, I say 1 ampere current is flowing. Now how much is 1 coulomb? Yes, we had seen these many electrons are traveling in 1 second. When I say 2 ampere current is flowing, I say 2 coulomb on 1 second. Is exactly double number of electrons will be flowing through given cross section. So anyway, ultimately we are coming closer to the Ohm's law. What does Ohm's law say? This current is proportional to EMF. Okay, if you increase EMF, current will increase. Okay, so in this way you got the two concepts. So EMF is what? I will just revise. EMF is amount of energy supplied to circulate unit charge once round the complete circuit. So EMF is joule per coulomb. But the memory of scientist volta, the unit of EMF is 1 volt. So what is 1 volt? 1 joule upon 1 coulomb. So when 1 joule of energy is supplied for the circulation of 1 coulomb charge, we will say EMF of the cell is 1 volt. Okay, so we have seen the relationship between EMF, drift velocity, and finally the current is. Now we just consider next topic, that is PD. Now we just discuss what is difference between EMF and PD. See, I have this pattern here, plus and minus. Now we are in the phase of discussing the ideal battery and practical battery. We just in further part of the discussion we will be introducing resistances. But here I will just keep in mind that every battery has got some internal resistance. Okay, so that is what the practical battery is. Ideal battery don't have any internal resistance. See, what we see outside is like this. We see the terminals plus and minus. What is there inside? Inside there is something called as an internal resistance of the battery, and here it is actually the EMF E. So when I connect some external circuit, some conductor externally, yes, we had seen that electrons will travel from minus to plus. But one thing we should remember, that convention direction of current is always from plus to minus. It is opposite to the flow of electrons. Anyway, so in future we will take the actual direction of current is from plus to minus, and we will keep in mind that actual flow of electrons is from minus to plus. So here it's a complete circuit. See, current is flowing, electrons are traveling. Now this conductor converts this energy into heat energy. So I can say that this resistive element. See, every conductor has got some resistance. So every conductor or a resistor converts electrical energy to heat energy. Now look at, so here this EMF supplies some energy. We have seen that EMF means what? Energy supplied. Out of that supplied energy, majority of the energy is spent here. It is converted into heat energy, and very much small amount of energy is spent here. That is why the battery gets heated. So this internal resistance we should consider when you are talking of the practical battery. So what you can say, plus minus E is the EMF. Out of that, the small r internal resistance, the capital R is the external resistance. So the voltage or potential difference available across this R is denoted by V, and a very few part of the energy denoted by V dash. So you can take the summation as E is equal to V dash plus V. V dash is what? It's a energy spent in internal resistance. V is what? Energy spent in the external resistance. So if you consider ideal battery, you can neglect this R. So if ideal battery is considered, most of the times in networks we assume the battery is ideal, so we neglect this R. So in that case, we have this type of circuit, so we can say V is equal to E. So V is known as a PD, potential difference. So when you measure the voltage here using the voltmeter, you are measuring the PD. Okay, you are not measuring E, because a few part of the energy is spent here. Anyway, if you are interested in measuring E, you can go for potentiometers. So generally we use a voltmeter, and voltmeter takes some current, so we are measuring V. Anyway, so if you are talking of the ideal battery, we can neglect this V dash and say V is equal to E. So this is about the EMF and PD. Now the next part we'll discuss what is the resistance. Basically, it is a opposition offered by conductors to flow of current. The more, you can say, a good word will be, this is just something which limits the current. So to oppose means to limit against. Now see, I have some conductor. This is a conductor. We have seen that current flows, electrons will travel in one particular direction. Suppose L is the length of conductor, area of cross section is A. Now this will be the path of current, and there may be some material. So you can say this opposition, that is the resistance, will be directly proportional to length. You can compare with the water pipe. More is the length of water pipe, more will be the resistance offered to the water. Now this resistance is inversely proportional to area of cross section. Yes, if area of cross section is more, electrons can easily pass. Just compare with the water again. So if you combine these two, you can say that R is proportional to L upon A. Finally, the proportionality constant, if you insert, it is rho L by A. This rho is what? Is a specific resistance, or also called as resistivity. It is called as resistivity. It depends on the material you are using. So, finally, this is important expression. R is rho L by A. So, you can say the resistance is directly proportional to length, inversely proportional to area, and again it depends on the material we are using. So, this rho will be different for different materials. For example, rho for aluminum will be something, rho for copper will be something, rho for carbon will be something. So, this is something, the property of material. If rho is more, you can say the given material is not a good conductor. If rho is less, you can say the given material is good conductor. So, when you are talking about the insulators, there are some materials which do not allow current to flow easily. This word easily is important. So, insulators do not allow current to flow easily because they have very large resistivity. That material is such that it opposes to the flow of current very much, to the large extent. Anyway, generally, when you are talking of good conductors, we say that the specific resistance is very less, and the best examples we observe aluminium, copper, silver, gold, and so on. But in, say, if you are talking of a very small wire of copper, see, this is a wire of copper, certain meters, few meters. So how will you calculate its resistances? It will be calculated by rho L by A. This rho will be fixed for given material. It is given in the data sheet. So, but if it is a few meter wire, this resistance will be very small. So you can say it will be something 5 ohm, 1 ohm, 2 ohm, like this. Very small. So a small wire of copper, generally used for wiring purpose, we neglect its resistance. So if you are going for major resistances, the material may be carbon, material may be metal oxides, metal films. Those are having very, you can say, large values of specific resistance or resistivities. So for that, even a few meter wire, if you take, it will be having large resistances of the order of kilo ohm, mega ohm, like this. So these materials are used for when you want to limit the current to a large extent, we may go for higher resistances. And in that case, the material will be used which is having large specific resistance. Now, this specific resistance actually, we take this rho is equal to R into A upon S. Okay. So if A is 1 square meter, L is 1 meter. In that case, rho will be numerically equal to R. Numerically equal. See, the unit of R is ohm and unit of rho will be ohm meter. So numerically equal to R. For example, suppose I will take a copper wire and purposely I will take a piece of copper wire of 1 meter length and area of cross section is 1 square meter. If current is passing this way, okay. So area of cross section is 1 square, length is 1 meter, and I will measure the resistance of this particular wire. Suppose it comes out to be 0.01 for example. In that case, rho is 0.01 ohm. This will be the rho of copper. So specific means what? Unit length, unit area of cross section. In that case, you measure the resistance, that is known as a specific resistance. See, this value will be used for comparison. Suppose you take a aluminium. See, this was a copper. Take a aluminium, 1 meter, 1 square meter area, and again you measure the resistance. Suppose it comes out to be 0.02 ohm for example. So I will say rho of aluminium is 0.02. Now you can see both are having same length, same area, still the resistance is different. Actually these values are not exact values. For exact value you should refer data sheet. Actually just I am taking for example. Now look at this. These copper and aluminium have same length, same area of cross section, but its resistances are different. Yet see that resistance depend on area, resistance depend on, see resistance is rho L by, resistance depend on length, resistance depends on area and material. Now for comparison, take the same length, unit 1 meter, 1 meter. Take the same area, 1 square meter, 1 square meter. And now measure the resistance. So it will only depend on the material. So this rho is something which tells about the material, which tells us about the resistivity of material. You can say it tells about the specific resistance of the material. So if you compare these two figures, you can definitely say that copper is good conductor as compared to aluminium because it is having less resistivity, less specific resistance. So when you want to compare the conductors, you have to go for this figure. Now good conductor means less resistivity and bad conductors means high resistivity. So you can compare with silver also. So if you compare with silver, you will find that silver is better than copper. So you can say that this is the best, this is better, this is good, better, best. But we cannot use silver for household wiring because the cost of silver is high as compared to copper. So for household wiring, we prefer copper. And for the big one, you can say for wiring of, you can say electricity poles, where generally aluminium is preferred because cost of aluminium is less as compared to copper. So this is about the resistivity and resistance and all that. Now we want to find out the relationship between PD and resistance and current, and that is based, explained the very fundamental law of electrical engineering, the Ohm's law. Now what Ohms has done, see, he has taken a battery. This is a battery. Now see, this battery, we can assume an ideal battery for example. So if it is E and this is V, so we will approximately say V is equal to E. So we are neglecting the internal resistance of the battery. So we can say PD is equal to EM for a time. And we can connect some conductor. Now this conductor, see, every conductor has got some resistance. So we show the conductor having resistance R. Actually, what is this? This is again a conductor. This is again a conductor. But we are assuming this is a copper wire. This is a copper wire. So we are neglecting the resistance of copper wires, and we are considering this may be a material slightly different than copper. Now, why we go for this particular resistive path? If suppose you connect a battery to a very pure conductor. For example, you connect a battery to copper with the help of, you connect the plus and minus with the help of copper wire. Now this copper wire of very small length is having very negligible resistance. It will have some resistance, but practically a small ideally will take a zero resistance. So if E or V is the PMF, or you can say PD or EMF, something like that, and if it is connected in this way with the help of a copper wire of very small length, it will be having very small resistance and very large current will flow in the circuit. Unlimited flow of electrons. Just like flood, you can say flood of electrons. And that flood of electrons will damage the battery itself. There may be sparking here. So we don't go in this way. We take something, and some significant resistance should be present. This may be a material of carbon, this may be a material of metal oxide, metal film, wire wound, anyway. So we have some resistance here, and this is connected to the battery with the help of copper wire, and we are neglecting the resistance of copper. So what is major part? What is major resistance? This is the R. Anyway, so in that case, so if this is a circuit actually. Now I will use some instruments. I will connect the ammeter. What is the use of ammeter? Ammeter will measure the current flowing. How ammeter is connected? Ammeter is connected in the series. Now I will connect the voltmeter here. Now you can connect the voltmeter. What is the purpose of voltmeter? It will measure a potential difference, PD. Now see, voltmeter is always connected in parallel in between the 2 points, and ammeter is always connected in the series. Now what is by series? Whatever current you want to measure, that should flow through ammeter. That is what known as ammeter is connected in series. So this voltmeter will give us a PD or EMF. We are neglecting internal resistance, so PD is EMF, and ammeter will give us reading of current. Now we can assume an adjustable battery. Adjustable battery means what? We can increase or decrease the EMF. Now practically, how we can increase the EMF? Suppose I have 2 cells, plus minus E1 plus minus E2. Now what will be the total EMF? They are cascaded in this way, minus plus, total EMF will be E1 plus E2. So we can increase the EMF of the cell by cascading the number of cells. So here I say the adjustable battery. Adjustable means we can increase the EMF or we can decrease the EMF. Anyway, we go on increasing EMF or PD, it is observed that current will increase. So the Ohm's law is current flowing through conductor is directly proportional to EMF or PD applied across it. Now see, provided, what is provided? It is also important. Physical state of conductor should not change. Throughout the experiment. What will have physical state of conductor? Will not change the length of the conductor, will not change the area of the cross section, will not change the material. Means what? Will not disturb this setup throughout the experiment. Even will not change the temperature of surrounding. That is also the part of physical state. So if you keep this physical state of conductor remaining same, now what is conductor? Actually this whole path is conductor. But we are neglecting the resistance of copper wire. We have seen why. Now we are just focusing on this. This may be something different. Anyway, this total path is conductor. Out of that, R is the resistance of the path. So this conductive path, we don't disturb. We go on increasing only EMF. What is observed? Current goes on increasing. Or we can say mathematically I is proportional to V or I is proportional to E. So you can draw the graph for one particular experiment. The graph is like this, I versus V. This graph is a straight line passing through the V. If V is 0, I is 0. Go on increasing V. I will go on increasing. So in another language, this V upon I is some constant. And that V upon I constant is known as a R, is known as the resistance of circuit. So this is what the mathematical statement of Ohm's law. Now this is one particular experiment when this R is kept constant. Now we can repeat the experiment. Suppose we change this R to R2 suppose. And again we draw the graph, again we go on increasing this E. We start from 0, go on increasing, we note down the readings of, see, voltage is shown on voltmeter, current is shown on ammeter. We get the same nature of graph for R2, but what has happened? What has happened? The slope will change. So this slope of the graph is actually function of resistance. Anyway, for a particular one experiment, this statement we can follow. Don't disturb the conductor, go on increasing, PD, current will increase. So, this is what the Ohm's law is. So, this is very useful throughout the current electricity, throughout the networks. Most of the other laws are actually dependent on Ohm's law. Anyway, so now we will come to a very basic network. See, this is a V or E. See, generally in networks we neglect the internal resistance of the cell, so we assume that PD is EMF. So it is EMF, it is a PD, and here it is a current. Now current flows from plus to minus, electrons flow from minus to plus. So we can apply the Ohm's law here. We can say that I is V upon R or V is equal to IR. Anyway, depends on your application. So this is a mathematical statement. Now we can note down that this E is a conductor having a ideal conductor having a zero resistance. Practically even copper has got a very small resistance. So this is your copper wire shown by the black lines. So copper. Okay. We say that it's an ideal one. Ideal wire is zero resistance. This may be different material. Maybe carbon composition, maybe metal oxide, metal film. So in market, we have a resistance which looks like this. In circuits, we use a resistor. You can see in electronic shop or electronic lab, it has got something like a color codes. Color codes are used to find out its value. So it looks like this. So this is this resistor. So if you see this circuit, practically it will look like this. I have some battery here, and this is my wire, and here I have a resistor. So this is a complete circuit through which current can flow. And if you are interested in measurements, you connect here ammeter. Instrument will measure the current I. You connect here a voltmeter like this. Instrument to measure the voltage. Look at this. Voltmeter is connected across the cell, across the plus end. Always voltage is measured between 2 points. So this is what voltmeter is connected in parallel. Ammeter is connected in series. And the conventional direction of current is this I. Now if you don't connect this, suppose you connect the battery plus and minus with the help of a very small copper wire of negligible resistance, what will happen? R of this is almost zero, negligibly small. And what will be the current? So current will be V upon R. So V upon 0, it will be infinity, very large, practically speaking very large. So that last current will damage the cell itself. This is known as short circuit. So we don't want short circuit. So we want the current. We want limited amount of current. We need a controlled flow of electrons. So there should be some resistive path present. You can say there should be significant resistance present in the path. So it will limit the current, and that current can be delivered by the cell. So this is about the resistance, Ohm's law, current and voltage and all that. Now, in most of the circuit we use a combination of resistances. Now, look at this. This is R1 and this is R2. Two resistors. How it will look like practically? So resistor looks like this. It has some color codes. Now this lead is made up of aluminium or copper. So you can neglect the resistance of this lead. The major material is here. I have another resistor of some different value, maybe. You just solder here and solder like this. So this is R1 and this is R2. Now, if suppose no other path is there and we have some battery present here, suppose current is flowing in this path. Same amount of current will flow. These two are connected back to back. No other path for current is available. Same current I will flow through them. We say that these two resistors are connected in series. Okay. So now what about the equivalent resistance? Equivalent means what? Suppose I have two resistors R1 and R2. They are connected in series, and I will connect a cell here. Suppose V is the PD. Now these two resistors will draw some current I. Now their equivalent means instead of these two, I will connect a single resistor to the same cell of PDV and same current is drawn. I say that this particular one is the equivalent of these two. Okay. Means now the question is how you will find this equivalent? So this R equivalent is simply R1 plus R2. If suppose n number of resistors R1, R2, Rn, they are all connected in series. Now how you identify whether they are in series? See, they should connected back to back. Means what? Start, end. Okay, like this. And there should not be other path for current to flow. Means there should not be other some path like this. This should not be present. So they are back to back and same current will flow through them. No other path for current. So they are in series. Now how will you calculate the equivalent? Simply R1 plus R2 plus Rn. This is a very simple formula. So this is what combination known as resistors connected in series. Anyway, now we move to another important combination, that is resistors connected in parallel. Now look at this. Suppose I have one resistor, another resistor like this. Suppose this is R1, this is R2. These are the leads. Now what I will do? I will join these two leads. Now what is this? This may be a very good conductor like aluminium or copper of negligible resistance. And I will connect these two. And from this I will take a wire, another lead, another conductor like copper or something like that. And I have this battery here, plus and minus of potential difference V. This combination is known as they are connected in parallel. Now it is very easy. You can easily find out what is parallel. Look at this. This is the start and end. Start of first resistor, end of first resistor. Start of second, end of second. Start shorted, end shorted. That is what you can easily identify. They are connected in parallel. So in networks, we generally use a symbol R1, R2, and we show this connection like this, and some cell. This is what a parallel combination. Don't confuse. Sometimes the drawings are like this also. Still they are parallel. Why? Because see, There starts and end, shorted, starts and end, shorted. Now how current get distributed in such a network? See, some current starts from here, suppose it is I, total current. Out of that, part of the current will flow in this direction, rest of the current will flow in this direction. One more important law we will discuss next time, that is KCL. You can say I1 plus I. This is a junction. Incoming current is I, outgoing currents are I1. And these two currents will meet each other here again and I current will come back. Whatever current that will start from plus, same current will come back to the minus. This will be always followed anyway. Anyway, this type of connection is parallel connection. Now what is the equivalent of parallel connection? How to find out the equivalent? I just write down the formula for that. Now what is equivalent? These two are drawing total current I. Total current I. Now I will take a single resistor, we call it as R equivalent. I will take a same battery, same PDB, and that draws the same current I. See, whatever the total current drawn from these two was I. Same battery I am using here. Same current is drawn, but this is a single one. So this single one is known as the equivalent of these two. Now the formula for that is 1 upon R equivalent is 1 upon R1 plus 1 upon R2. So this we can simplify as R equivalent is equal to R1 into R2 upon R1 plus R2. This is what simplified formula for two resistors connected in parallel. There may be three resistors R1, R2, R3 connected in parallel like this. And we are interested in equivalent of these three. The formula will be 1 upon R equivalent is 1 upon R1 plus 1 upon R2 plus 1 upon R3. Like this. So this is about the equivalent resistor, resistance of parallel combination. Now, in some networks, we have combination of this. Suppose I have this network R1 and R2, and here it is R3, R4. And this is what the supply is. Now we are interested in finding out the equivalent of these particular combination. Now how will you solve this? You can note down these two are in parallel. So you can find out the equivalent of these two. Suppose this is R1, this is R2. And equivalent of these two will be suppose R equivalent. Now how will you find out that R equivalent? It will be simply R3 into R4 upon R3 plus R4. You will draw the network once again and again you will see the network. Now you can observe that all these three are in series. Why? Because same current will flow, they are connected back together. And finally the R equivalent final. Final is what? Combining all these three. I will say R1 plus R2 plus R equivalent. This is the total equivalent of this particular combination. So you can try for some more networks where you will find the complex network. You can find out the equivalent of that.